Sure. Thanks for me. I'm really honored to chair this first uh, panel session. Actually, this conference is becoming a very nice tradition in our community. So I'm starting sharing my few slides. I'll try to give my introduction short because we have amazing talks following. My talk is about embodied intelligence and its relation with soft robotics, actually. I'm sure I don't need to define embodied intelligence too much in this community, but I just wish to recall the reasons why we consider it very interesting in robotics and why it is so important for soft robotics. And the reason for us is that if we consider embodied intelligence, adaptive behavior emerges from the interaction with the environment. So we don't have to program our robots too much. So many tasks become much easier if we take embodied intelligence into account. And as Fumi already presented in an ideal sensory motor scheme in a robot, the important part, if we consider embodied intelligence, is the blue one. And especially this arrow, which is the mechanical feedback from the environment. So in robotics, in order to grasp this, we need to be able to use this interaction from the environment. So we need some compliance in the robot body. And this is what led to soft robotics, actually. So to robots that can undergo large deformations when interact with the environment. And I also want to start with the summary from my first talk in this conference in the first edition, 2021. Actually, I called it Joys and Sorrow about the use of embodied intelligence in soft robotics, because I think there are a few trade-offs that we are still looking for in soft robotics when using embodied intelligence. For example, we know that embodied intelligence work in a specific ecological niche, and sometimes this niche is quite small for robotics. So the passive worker is the typical example that we use to explain this, but in robotics, we want our robots to do more tasks. So we need to be able to implement multiple ecological niches and also cognition in our robots. On the other side, what's exciting in embodied intelligence is that we can simplify the control of our robots in terms of control parameters. But at the same time, as robotics is as soon as we design a soft robot like this one, especially if it has an arm shape, we want to control it precisely. We want to control the end effector. So we say, okay, but it's difficult to control it in the traditional way. So this is also a trade-off that we need to find. And then we said that we simplify the control of our robot behavior, the sensory motor behavior, I mean, but it works. The embodied intelligence simplification works if we take into account the morphology, the mechanical properties of the robot body, the interaction with the environment. So the design of the robot becomes more complex, in fact. And we still have a lot of nice principles for embodied intelligence, but not really an abstraction and mathematical description of them that we can use in robot design. So those principles are in most cases learned from biological models. So in my own research, we have been learning a lot from the octopus. For example, we found nice principle for underwater grasping. It's a very efficient movement where control is very much simplified because of the interaction with water. And we are trying to demonstrate quantitatively that how it works and how it happens. We learned about how we can walk underwater with legs and how we can swim with this pulse jet propulsion, which is very, very simple to control. Basically, control is really minimal in all those cases. But how can we put all this inside our robots? So how can we design soft robots with embodied intelligence more systematically? As we said already, embodied intelligence is basically in this arrow. So my question is can we fully capture embodied intelligence if we can model that arrow? So if we build a complete mathematical models, not only of the soft robot internal interaction, which is what we are used to in robotics. So it's the model of the deformations given by actuators, but coupling them with external interactions and model of the external interactions. In a relatively simple case like our octopus here, there are already many challenges. The problems are multi-physics, multi-scales, and we want, as I mentioned, to couple internal interaction models. So what the actuator forces generates in the soft body with external interaction models. So what the external forces generate in the soft body. And this external forces can come either from solid contacts or interaction with fluid, like in our octopus case. So we think that actually we can try to put this into a very general mathematical framework where we just try to couple of all these models. So we may describe what happens with soft robots. So with this differential operator of this term describing the soft body. With a nonlinear term that describes the mechanics of the soft body, and then two coupling terms. So the first one accounts for internal interaction. So as I said, it's the action of actuators on the soft body. We are a little bit more familiar with that in robotics because this is what we need for implementing control in our robot. And this other coupling term that instead accounts for external interaction. So as I said, either contacts with external solid, which is relevant for locomotion, for example, or grasping, or interaction with fluids like in the swimming hole, all these in the soft body domain. So depending on the kind of approach that we want to use for developing such models, the terms in the equation assume different forms. But the message is that there are actually techniques that we can use, and generally speaking, we can either they can either be in the realm of 3D continuum mechanics, or in the case of internal interaction, we can use other possible approaches like rod models or either finite dimensional parameterization models. For the case of external interaction as well, we can either take approaches in the realm of continuum, either fluid mechanics or solid mechanics, and approaches based on lumped parameters, again, in both cases where we sort of simplify and concentrate some key parameters in a few terms. So again, depending on the kind of approach we take, we can give a different form to the terms in our general equation, but actually it describes completely this coupling between internal and external interaction. And this is just an example. It's actually quite old, but here you see the coupling between the deformations given by actuators and the deformations given by the fluid dynamics, so the interaction with the fluid, and this is based on lumped parameters approach. So all these can actually bring to model-informed design of soft robots that embed embodied intelligence. This is something that, I mean, the use of a model-informed design, computational model, has been happening in other fields. What you see here is the number of the percentage of papers with computational modeling in different disciplines. So aerospace is in blue. The black line is a reference for all literature because the use of computational modeling has been growing on all disciplines actually. So in aerospace, we see that we have a growth, and this corresponds to a growth over the field itself, from the beginning of civil aviation to the Apollo program that gave a boost and brought to a steady growth, up to the reality of today, where we have a space tourism already, and really hundreds of thousands of civil flights every day. So what I am arguing is that we may be at sort of Apollo years for soft robotics if we can do this transition to model-informed design of soft robots, and then bring the disciplines to a tangible societal impact, something that have been discussed and has been discussed in our community recently. There is also another aspect that I really like of the advantages in using embodied intelligence. I think that computational efficiency is really the very first step towards sustainability. We want to make robots more green and more sustainable, but I think that we tend to forget that digital processing computation has an energetic cost, and it has an impact on pollution. And if our robots are more computationally efficient, we can actually reduce their energy consumption. Nature gives us a lot of elegant, computationally frugal solutions, and embodied intelligence is definitely one of them. So if we reduce the energy needs of our robot, we can also think of some other ways of powering our robots, and we may think of having them finding energy in the environment with some sort of recovery, energy recovery, scavenging mechanisms. And of course, it has to be coupled with biodegradability, or at least recyclability. But this is also very, very good with soft robotics, because we made this profound rethinking of materials for building robots, so we can definitely investigate how to use biodegradable materials here. And this is something we started in our university, especially for marine applications, where this aspect is especially relevant. So my news summary, it's a bit more positive than the one I started with. So embodied intelligence is definitely one of the major lessons that we can take from nature. And as I said, in robotics, this is exciting for simplifying the control and make our robots be complex, with complex behavior in complex environment, but simple to control. And maybe we can really grasp embodied intelligence if we can couple mathematical description of internal interaction with external interactions. And this would bring a leap forward of soft robotics as a discipline toward model-informed design. And finally, this can also improve the sustainability of robots by reducing the computational cost, the energy needs, and with the use of energy scavenging method. So I, first of all, thank you for listening. I thank the funding agencies behind my research.